Okay, cool. So let's get started. Good morning, everyone. Uh, well, as I said, I want to show you today how to profile your programs and understand how hotspots and other metrics associated with your programs. And for that, I should be able to connect to my office desktop using the remote desktop option, but I couldn't set it on time. So we are joining here remotely. So in the last class, we have seen how to use SIMD instructions to get performance improvements in our code. Uh, and in that context, no, especially, and we saw how to do vector addition using SIMD instructions, and we got some speed up. So there is a question and from one of you, forgot your name. So that is, if you go and look at the processor, all the instruction sets supported by the processor, it says multiple things. And how is it possible that the same processor can support multiple instruction set architectures? Who raised that question? Can So let me share my screen. Um, so between, please feel free to stop and ask, no, raise your hand and ask any question that you may have. Uh, you're able to see my screen, right? Okay. So that brought CPU info. If you see here on my last class, I have shown that so among the flags, AVX2 is there. That means the processor on my desktop, it supports AVX2 instruction set. AVX2 instruction set means what is the how many bits, what is the size of the vector registers, how many floating point operations we can do in parallel. How many floating point operations we can do in parallel if we have AVX2 instruction set. Single precision, 8, yeah, we can perform 256 bits. The length of the vector register is 256 bits. And we will be able to perform 8 single precision full floating point operations in parallel. Okay, each floating point operation, it has 32 bits. So 8 into 32, 256 bits. So overall, you will be able to perform 8 floating point operations in parallel. And you can see, we can also see along with AVX2, there could be something like SSC 4, SSC 3, and a few other instruction sets. So the question for you is, how is it possible that the same processor can support different instruction set architectures? Like, for example, you can see here SSC and SSC2. SSC and SSC2, they could be uh, I don't recall, they could be 64-bit vector instruction, 64-bit or 128-bit vector instruction set architectures they could be. So how is it possible that the same processor can support different instruction set architectures? To kind of to kind of give a bigger picture, so like if we have a multi-core processor, and if there are four cores, there are four cores present in the processor. So these are all four cores. And if you see every core, so let's say this is the part, uh, this part of the core that corresponds to the vector instruction set architecture. And this is a regular core, sequential core. This is a sequential core. This is a SIMD unit. So what happens is your regular instructions like add, subtract, branch, and those instructions, they will go to the regular sequential core. And this instruction set architecture, what is the instruction set architecture supported by this core? Let's say on Intel processors. What's the instruction set architecture supported by Intel processors on the regular cores? Anyone else? I want you to kind of pitch in, talk, otherwise, the class gets boring. It's more precisely, it is x86 underscore 64. Okay, at least on my machine. So it is x86 underscore 64. That is the instruction set architecture that is supported by the sequential core. And the SIMD part, it can support SSE, SSE2, so on up to AVX2. So Intel processors, when they design, they want these processors to be backward compatible. So if you take a processor which supports AVX2 instruction set architecture, then my guess is they will also support programs written using SSE or SSE2 instructions. Because when you buy a latest processor which supports AVX2, you want the previous software which uses previous instruction set architectures, we should also be uh, able to run them. Okay, so this is what is called as a backward compatibility. Backward compatibility. But on the flip side, you will not be able to support. You take a processor which has only AVX2 in support, and you will not be able to run programs, instructions using AVX512. It's not possible. Okay. So to summarize, so if you take every processor, Intel processor, if you consider, if you take a dual quad core processor, it has four cores. Every core has a sequential part which executes regular x86 underscore 64 instructions. And there will be a SIMD part. And the SIMD part, depending upon the processor, the instruction set architecture supported could be anywhere between SSE to AVX512. And usually what happens is, if this is the latest generation, if you take a processor which supports AVX2, then all the previous generation instruction sets will also be supported. So that is how things work. So you are with me so far? Till this point, you have any questions from the last class? Or how many of you checked your processors and figured out what instruction set architecture, SIMD instruction set architecture it supports? Can you put in the chat box everyone who checked your processor and try to figure out what is the instruction set architecture, SIMD instruction set architecture your processor supports? Can you type in the chat box, please? Monish has AVX 512. So, Monish, what is the processor you have? You are supporting those who have AVX 512. Pawan also has AVX 512. Don't send direct messages. Put your messages to the whole group so that everyone can see. 11th generation i5. No? Okay, great, great. Nice. Okay, so majority is AVX2. That is good. Good, very nice. Okay. So Pawan also has 11th generation i5 AVX. Great. Okay, so now what we will do is in the last class we looked at a very simple example, vector and code. And so now in today's class, we will look at a slightly more challenging problem and see how to uh, see the code for it and try to understand that code, how that code is vectorized. Okay, so let's see. Let me share my screen. It's already shared, but I think I have to clear this. How do I clear this? Okay, great. Yes. So the problem that we will be looking at is what is called as an image convolution operation. So if you see this picture, let's say we have an image is, like for example, an image is a two-dimensional arrangement of pixels. And every pixel value, it will range between 0 to 255. Okay. And so here we apply what is called as a convolution. So here, like for example, if you take the image here, and on this image, we are applying a 3 cross 3 convolution. So what happens is you place this filter on the first 3 cross 3 grid and you generate the first pixel of the target image. And we keep sliding this filter across the whole image. Okay, this is going a bit fast. But if you see, you can see this filter, which this is 3 cross 3. This is the filter. And this filter is placed at a particular position on the image, and we multiply the corresponding elements and sum them up. It's essentially two-dimensional dot product. And then if we generate a pixel, and that pixel, here it turns out -8 is what is obtained when we place this 3 cross 3 filter in the top left corner of this image. And then what we will do is we slide this filter one position to the right, and then again we apply this convolution operator, and we generate the next pixel here. Okay. What's the advantage of these image processing filters? If you see, like for example, these filters are useful in kind of doing image processing stuff. Like for example, here, this is the input image, and if you apply this convolution kernel on this image, we will be able to extract the edges from this image. And in fact, the whole deep learning stuff that perhaps at some point you will learn is how to apply multiple complex convolutional kernels on an input image so that we can generate different kinds of feature maps. So what we are looking at now is very fundamental to the computational problem that we are looking at now is very fundamental to image processing. And it is also an extension of this is fundamental to modern deep convolutional neural networks. Okay. So you can see naturally when we place this convolution kernel and move it around, uh, the number of rows and columns decrease by a factor of one because uh, yeah, so because you will, in order to kind of save on it, sometimes what we do is if you want to retain the target image size as same as the original input image size, we usually paired up no, these boundaries with zeros. Like for example, we will put 0, 0, 0, 0 like this so that the dimensions of the input and output images will match. Okay, so that way it is nicely possible for us to keep this kernel like -1, 0, -1, -1, -1, -1, -1, -1, and then this corresponds to generating this particular pixel. Yeah, it's not my picture is not accurate, but I hope you understand. So this is what is called, there are different padding strategies. This particular padding strategy is called as a zero padding strategy. You take the original image and you pad it up with zeros on all the boundaries so that when we move the convolution, it is possible the dimensions of the target image will be the same as the dimensions of the input image. Are you all with me so far on the problem, the convolution problem? Yes, no, can you put a message so that I know what is happening? Okay. Next. Okay, so now I think I posed this problem in the last class itself, and I asked you to check how we can go about vectorizing this problem. Anyone try to solve this problem and come up with a SIMD algorithm to for this? Did anyone give it a shot? Okay, it's like you didn't give it a try. So it's all right. Let's see how we can go about vectorizing this problem. Okay. So let's go and take a look at this code. So this is the program. And so here on line number 64, we are allocating memory for the source image, uh, which so usually the image, the original image could be each pixel in the original image could be bytes. But for the sake of simplicity, let's assume no each pixel in the original image is represented as a floating point number because after applying the convolution anyway, it becomes all the data has to be converted into floating point representation. And the destination is also of the same size, width times height times this. And we are applying a simple averaging filter. This is a dummy filter where all the coefficients are 1/9. There are 9 pixels. Remember, this is a 3 cross 3 pixel, 3 cross 3 kernel. And if you apply a simple averaging kernel, what will the output image will be like? What will be the output image will be if you apply a simple averaging kernel? You take a image and you apply a simple averaging kernel, then output will be a bit blurred. Okay. So now what will happen if you take the original image and subtract the blurred image from the original image, what do you get? If you take the original image and from that original image, if you subtract the blurred image, you what do you expect to get? Any guesses? A sharpened image. Yeah. Think about it. You can give it a try, perhaps. Okay. Good, good. Thank you, Faisal. Thank you, Arshit. So, and then on line number 69 to 71, we are filling up this image with a dummy image. Okay. You can use OpenCV benchmark to actually, sorry, OpenCV library to actually load a read an image and apply these filters and see what happens. But for the time being, we are not using them because our focus is actually on how to speed up computations. So we are not we are just going with a dummy code so that we focus on the computational part here. So now what we are doing is, we are applying this uh, this filter on this benchmark in two ways. When we call this benchmark function with parameter 0, then that means we just use regular for loop we use non-SIMD instructions to apply to perform this convolution operation. And if you pass one, then we use the AVX2 instruction set to uh, perform this convolution operation. So let's go ahead, and if you look at the benchmark function, are you all with me so far? You're okay? So now, so here, if so the parameter here, if you see the last parameter to the benchmark is use SIMD or not. If it is equal to 0, then we don't use SIMD, and if it is equal to 1, we use SIMD. And that's what we are doing on line number 48. We are checking if you would like to use the SIMD. If use SIMD flag is equal to 1, we call this AVX2 function, convolution underscore AVX2 function. And if it is equal to 0, then we apply a basic convolution. In both the cases, we get this time, and we compute the wall clock time. Okay. So this is, and since here, the total number of, in order to compute on line number 56, you can see the total number of operations that we are performing. It is written as width into height into 9. That is because when we place a convolution operator at a particular position, we are applying 9 multiplication operations. But this is a bit debatable. Why is this debatable? Do you think total number of operations on line 56, is it an accurate calculation? On line number 56, we are computing the total number of floating point operations that we are doing. Is it a accurate number? So Arshit says no. Why is it, Arshit? There are overlapping. Overlapping is not a problem because even so, why is overlapping is a problem? Yeah, overlapping is not the problem. More than there is no overcounting happening here, Faisal. Yeah, more reasonable thing to say is what Archit said. We are performing 9 multiplications and 8 additions. Okay, so there is a bit about padding, but in this particular case, we are not doing padding actually. So that's okay. Yeah, so padding may add a little bit more extra, but more importantly is for every convolution, we are performing 9 multiplications and 8 additions. That's exactly the case even in dot product also, right? In dot product also, when we want to compute dot product of two vectors, there's a multiplication and addition. We have to consider both multiplication and addition as different operations. So Faisal, think about it, just because it is overlapping, even if there is an overlap, we still have to do the complete calculation because it's a different computation. Okay. So now let's go ahead and try to look at this code. Okay. I'll give you some time to look at this code and understand. What did I do? Sorry. Want to post this. Yeah. I want you to take a look at this code, basic convolution code, and see if it makes sense for you or not. I'll give you some time and then I will explain. If you understood the code, put a message understood. There are 67 students. I really want to see that all of you participate. So what we are trying to do is good. I think many of you are able to understand what is happening. Okay. So this is the target image. And what is the y dimension here? So y goes from here to here. And no, x from here to here, we go in x. Okay. And what we are trying to do is that means we are computing the target image one row after another. So first you go with row one, and then you compute all the pixels of row one. And then after that, you go to row two, and then you compute all the pixels of row two, so on and so forth. So in row one, what you do is in the basic, you compute one pixel after another. You first compute this pixel, followed by this pixel, followed by this pixel, followed by this pixel. Okay. And in order to compute this pixel, and that's what we try to do, each pixel is computed using the code that is present here. Okay. And this is where the convolution operation is happening. So like, for example, here, let's say we are, let me use a different color. Yeah. So let's say we are here. So this is x comma y. Okay, this is so this is x comma y. So in order to kind of this how do we get how can we index? This is the destination image. How can we get the pixel here? For what values of kx and ky will we be able to access this pixel? For what values of kx and ky will we be able to access this pixel? Can someone put it in the message? You understood, right, the question? Yeah, so when kx and ky are equal to -1, then what happens is we will access this pixel. And so essentially when ky is equal to -1, and for different values of kx going from -1, 0, 1, we will be traversing these pixels like this. Followed by that, we do this. Followed by that, we do this. So we are computing the dot product row by row, and finally, the accumulated sum is assigned to the destination. Okay. Are you all with me here? Many of you have already understood it, but if anyone requires a bit more explanation, you can ask. All good? Anyone has questions here? So a very simple way to understand here is we are computing different pixels of the target image using the outermost two for loops. Okay. Once we enter the body of the second for loop, then x and y coordinate of the target image is fixed. And then what we do is we simply using this loops inner loop 11 and 12, we are just applying that 2D convolution. And once we are done with the 2D convolution, we are storing it in the target image mix. And that's all we are trying to do. So now, so this is, if you can see this code, this is a 4D loop. Okay, this is a loop with four loops, one inside another, and that is where things becomes very challenging for the compiler. So if you take this code and give it to the compiler and ask it to automatically vectorize this code, that is apply SIMD instructions to speed up this code, then it is going to be extremely difficult for the compiler. The compiler will not be able to do this job most likely. Okay. Now the question for you is how can we vectorize this code? How can we vectorize this code? That's the question for me. So to be honest, when I thought about it initially, it's not at all clear to me how we can vectorize this code. First question is it possible for us to vectorize the convolution operation? That is, you take the image, this 3x3 filter, and when you place it at a particular position, there are 9 multiplications and 8 additions happening. Is it possible for us to vectorize this operation? I'm seeing yes. How can you vectorize this operation? Can someone explain how can we vectorize this operation? So many people. Aditya, Nadine, Ameya. Arnav, so Arnav is here, so let's ask Arnav. So Arnav, do you think we can vectorize this convolution? We can do the multiplication in groups of 3 floats. Okay, that's a good idea. So there are 9 multiplications, and okay, one row you can so you will be able to get a 3-way parallelism. That means you can do 3 multiplication operations in a single shot. So there are 3 rows you can perform 3 multiplications. All the multiplications within the same row you can perform. Great. Any other? Two vectors each having 3 numbers. Two vectors each having 3 numbers. Oh, okay. That's what it is. Okay. Is there any other? Is there any other way where we can make this better than this? Any other ideas? At the first shot, we don't quite get it. Actually, it's very uh, okay. So now what I will do is I will show you the code and then see if you can look from the code. You will be able to figure out if it's possible. Okay, let me take this. Now, can you take a read? Can you read this code and tell what is the kind of parallelization that is being done? I'll give you 5 minutes. Loading 8 floats at a time and performing it together. Okay. I want someone to tell in a single sentence what is being done here. What is being done here in a single sentence. You don't need to tell all the details, but what is the high level parallelization idea that is applied here? Very cool idea. Anyone? So if you see, um, what is happening is, let me take a different color. Not, yes, yes, super. Perfect. Someone who got this. So Monish, what Monish is telling is so there is we can kind of call uh, what is called as let's say we have two kinds of parallelism that are available. Intra-convolution parallelism, intra-convolution parallelism. So this is the case where that's the suggestion that you gave earlier, where there are 9 multiplications overall. You do 3 multiplications in a single shot. So you do that, in 3 iterations. That is intra-convolution parallelism. So there you will not be able to exploit fully the available uh, parallelism given by the hardware, because you can do 8 floating point multiplications in parallel, and yeah, but unfortunately we are only able to use only 3 floating point multiplications when we try to exploit intra-convolution parallelism. Okay. The second parallelism, we can call it as interconvolution parallelism. And this is what is happening, that is in interconvolution parallelism. If this is the target image, okay, if this is the target image, so these are the rows, y is going from top to bottom and x is going from left to right. And so what we try to do is we try to compute the first 8 pixels, okay, 8 pixels, 8 target pixels in a single shot. Okay, like for example here, so we can keep going like this. So there are, let's say up to here, there are 8 pixels. This is output image. So what we try to do is we try to compute all these 8 pixels in a single shot. Okay, and that is what is happening. You can see here on line number 24. So we are incrementing the column one by a stride of 8. That means you render the output in every row In every row on line number 23, read it as every row. And in every row, you render 8 pixels at a time, and you go and render the next 8 pixels at a time, so on and so forth. And how can we render these 8 pixels at a time? So the way we render these 8 pixels at a time is, so you, like for example, just take for the sake of simplicity, these are the two source windows extracted from the input. Okay. These are the two source pixels extracted from the input. So what we do is we will have a vector register. Okay. So we will have a, yeah, let me make it more simpler. So we will have a vector register. What it does is it loads from the input image, 8 pixels into this vector register. Okay, there is this. Let me redraw this. Finding it a bit difficult to draw here, but I'll give it a try. So this is the output image. Let's consider the input image. This is the source input image. This is the source input image. Okay. Keeps going like that. So what we do is we take the first 8 pixels here. We take the first 8 pixels here. This is the 8 pixels. This is the input image, 8 pixels. And what do? We transfer these 8 pixels into a vector register. We transfer these 8 pixels into a vector register. And that is what we are doing on line number 28. We transfer these 8 pixels into the vector register. And this register name is pixels. That's what we are using here. And then what do? We use what is called as a broadcast operation on line number 29. The top, if you take this filter, let's say the filter, this is a 3-cross filter, and the value that is present here is 4. We copy this value 4, we broadcast this value 4 into this another vector register. This is the filter val register. And then you multiply these pixels with this filter val, and you store it in this, and you accumulate it in this sum register. Okay, and you accumulate it in the sum register. That's what we are doing here. This is step 1, this is step 2, this is step 3. Okay, so now after one iteration, so what do we get? We get a partial sum of the pixel here, and pixel here. We'll just get a partial sum. Now in the next iteration, so what should we load in the next iteration? In the next iteration, what we do is, we move this window. I'm using a different color. So we take this window and we copy this to this register. And the filter val register, instead of 4, whatever the value, let's say here, we have value 2, we copy 2 into this register. Okay, this is what we will do. Again, we will do the product of pixels and filter val, and then we accumulate it in the sum. And in the third iteration, what we do is, we take, so we move from here to here, we load this next 8 pixels into this pixels register, and then let's say the value that is present here is 3. We just copy 3 into this filter val, and then we, multiply them and accumulate. So what happens is in 9 iterations, this is, if you see here, in 9 iterations, at the end of 9 iterations, the sum register contains the complete value that should go into this 8 pixels of the output image. So finally, what you do is on line number 33, we transfer the contents of the sum register into this particular location after 9 iterations. So using this process, we are able to get 8-way parallelism. That means we are able to use the SIMD bandwidth completely. Are you all with me here? How many of you understood the approach? This idea of interconvolution parallelism. Everyone with me here so far? This is a cool idea, no? How many of you thought it's a cool idea? I felt it's cool because I didn't get this idea when I thought about it. I thought it's going to be. I was also thinking in the intra-convolution parallelism approach, but then when I saw this thing, no, it's that interconvolution parallelism, it makes a huge difference. Okay, nice. I will post this code after today's lecture. I would like you to read this code and understand more carefully and see, how this whole thing is working. Anyone has any questions? Let we can run this program and see how it is how much speed up we are able to get. Okay, let's run this code. Yeah, so Monish has a good idea that since the filter array is constant, wouldn't be better PSS, Monish? That's a further optimization is on line number 29. We don't need to keep reading the filter values again and again and again. So we can kind of optimize on that front quite a bit. Okay. Ameya is asking, can you also send references for the same to read? Unfortunately, there are not many references, Amaya. I will try to see. So that's the reason I'm asking all of you to understand these things in the classes because these are not properly present in any particular book or place. But I'll try to uh, but I'll try to look for references and send. But you should be able to understand by just looking at the code. I will post this code and the discussion in the class and the code, you should be able to understand what's going on. Okay, now let's see. Now let's try to compile this code and see where. More file. I didn't write a proper makefile for this. So now if I use dot on it, so the non-CV, so we are getting how much speed up we are getting? We didn't actually compute the thing, how much speed up. I can say 1.7 divided by 0. Yeah, we are getting 0.4 times speed up when we look at gigaflops. And if you look at the time in milliseconds, it is 35.0 milliseconds divided by 1.7 milliseconds. No. Is there something wrong? It should be 0.35. 0.35 divided by, let me use the other way. 1.5 divided by 0.35. Yeah. So you can see that, the ratio of the gigaflops and, this is very close. So 4.25 gigaflops, if you are able to increase the gigaflops per second, then automatically the compute will get corresponding speed up. Okay. In fact, I would say in this particular case, the gigaflops number, it is not accurate. We are able to get around 3.5 gigaflops per second because we are only counting for multiplications, but we should account for additions also. Okay. So far, so good. You're all with me? So far, happy? Makes sense, this code? So many times, when we want to get very good speed ups, using SIMD instruction sets is very, very powerful, but using them is not easy. That is the primary thing. Okay, it's using SIMD instruction set is not easy. We have to be very creative in using the SIMD instruction set. And what we are looking at is relatively simple problem to kind of vectorize, but there will be more complex codes which will be that we will encounter in practice, and solving them using SIMD instruction set is a bit of a pain. Okay. So now what we will do is in the next class, we will change gates in the second half of now for the next half an hour. We will study, we look at what is called as program profiling or hotspot analysis and things like that. And in the next class on Monday, we will see much more involved example for SIMD, much more involved SIMD vectorization problem. So now we will kind of make it slightly more lighter, and we will look at how to do performance, hotspot analysis. So now the question for you is, given a program for you, and how do you go about optimizing that program? What would be your step 0 or step 1? If someone gives you a program for optimization or software for optimization, what would be your step 0 or step 1? Use compiler flags. Faisal wants to use compiler flags. Good. What else? To find whether it is compute or memory bound. Great. Find bottleneck in code. Okay. How do we find this bottleneck in the code? Is it possible for us to get an estimate of speed up? Hey, this is the code, and perhaps we might be able to get 2x speed up or 3x speed up or something like that. Is it possible for us to get some kind of estimate, speed up estimate like that? So before given that, yeah, so Prakhar said find bottleneck in code. How do we go about finding bottlenecks in the code? We could time different sections of code separately. Okay, awesome. Yeah. So that is what is called as profiling. Okay, but the problem is, let's say if you have a software with 100 functions in it, okay, or 1,000 functions in it. Do you think is it possible for us to put to time different sections of this code when you have a code base with some 1,000 functions? How do we solve this? Did anyone use any tools before to solve this? Yes, yes. So we can use, so there are 3 interesting tools suggested. All are very nice. Thank you. Insight Compute. Ansh, I didn't hear about it. So, but at least One thing is, what is the first thing? We can use gprof. Second thing is per. And what is the third one? Third one is, yeah, Valgrind. Yes, Valgrind. I used all three of these, but the fourth one, which Ansh suggested, not sure. I will take a look into it. Okay. So we will now see how to use gprof. It's not a very difficult thing. We have, but it's let's for the sake of completeness, we will see. Let's say, for example, I have a code like this. Okay, let's cd hotspot. So I have this code more hotspot underscore demo.c. So in this code, let me open it using the, yeah, maybe I will use it using Vim. So here there is this main function. The main function, it calls this function called as heavy calculations on line number 30. It passes some number of iterations, and then there is one more function called as factorial function, which is being called. Uh, so, uh, so if you see, this is a kind of a 2D loop. What happens is, as the as iterations increase, the time increases quadratically. Okay, so CD is equal to 24. Let me just so in order to profile this code, so we have to compile this program using this option called as -pg hotspot demo.c -o hotspot demo. Okay. So you compile this program. When you compile this program using these options, the generated executable, it is instrumented with some counters so that when you run the program, those counters will be registered. Okay, like for example, if you run this program hotspot demo, then what happens is you will see that there is this file called as gmon.out is generated. But, yeah, let's see. It doesn't have anything interesting, but let's see how more. Let's see what is the command that we use. Okay. So now what we do is we use this command gprof hotspot demo gmon.out greater than analysis.txt. So now if you see this analysis.txt, it contains all the profiling information. Like for example, it says, the overall, that 62, almost all the time is spent in this particular function called as heavy calculation. And, it takes 0.62 seconds, and 100% of the time is spent in this function. And you can see here main takes 0.62 seconds, and the time spent in main is negligible because almost all the 0.62 seconds is taken by the heavy calculations program. Okay. So while this is a kind of a trivial small program, which may not be a big deal, but if you have a big code base with 1,000 functions, for example, then it is possible for you to see what is the percentage of, what are the functions that are being called, and what is the percentage of functions, what is the percentage time spent in different functions. So in order to get the kind of visual result, we can use what is called as a gprof to dot of, yeah, so if you see here, so you can use what is called as a gprof2 dot tool, so that we will get a visual information of, we can visualize the profiling results. So let's call this function, call this target, make call graph and dot. Then what happens is, there is this file called as output.png generated. This contains this profiling information, this hotspot analysis information as a in visual format. So if you see here, this is output.png. This says no main calls heavy calculation, and most of the time is spent in main in the heavy calculation, and that is how this graph is printed. So again, this is a trivial thing, but because it's a very small program, but if you have some thousand functions, and when you do a gprof and be able to plot this call graph, then immediately you will be able to figure out what are all the functions where you are spending the maximum amount of it. Are you with me here? Yes, no, maybe? Let's clear this. Okay. This also, we will look at more sophisticated tools in a moment. But what I want you to see is, so if you go look at this, there is this tool called as, there are many ways of profiling your code. Like for example, if you see, you can profile your code using what are called as Linux performance counters. So you can profile your code using performance counters, and once you get the results, then again you can use this tool called as gprof2 dot, using which you can generate, visualize the profiled information cleanly. Okay, so there are different ways to profile your program, OProfile, Expert. There is what is called as a V-tune amplifier, which you may end up using in this course. And right now, this is what we have used. We use gprof to profile our code. And once we have profiled our code using gprof, we are redirecting that input to this gprof2.py tool. And it generates a PNG, and it generates a dot file, and the dot file is converted to PNG by using this dot. Okay, this is what we try to do right now. And I want to show you some cool things here. Like for example, yeah, this is what I wanted to show. This is the profiling information. If you see the diagram here, this is a detailed profile information which we are able to plot for some complex data, for some complex program. By looking at this program, by looking at this graph, we will be able to identify what are all the hotspots in our program. So given a program, the first for performance improvement, the first thing that we would like to do, now, can you tell me what we should be doing? The first thing that we should be doing, given a program? Anyone? So we have to do profiling and hotspot analysis. So this is the place where we start here. So now a question for you, which I would like you to answer. Let's say you have there's a program in which you have seen that 50% of the time is taken by one particular function. 50% time in let's say function f. Now, if you optimize this function f, if you try to focus and optimize this function f, what is the maximum speed up that you can expect for your program? if you optimize your code, super optimize your code by optimizing F. Okay, what is the maximum speed up we can get? So if you take, the original program takes 100 units of time, and out of that 50 units of time is taken by the rest of the program, and 50 units of time is taken by this function F. So if you super optimize your function F, and make it equal to make this 50 approaching zero, then the best max speed up that you can expect is 2. Max speed up uh, is 2. This is the best that you can get. So this is a very important observation. But instead of 50%, let's say if it is 25%, your code is this function F takes 25%, then what is the maximum speed up that you can expect? What is the maximum speed up that you can expect? Yeah, 1.33. So if it is so then what happens is if it takes only 25%, then what happens is this looks like 100 by 75 plus 25, and this 25 can tend to 0. But the speed up that you can get, this it will be 4 by 3. Okay, so this is the best that we can expect, which is nothing but 1.33. Periodically here so far, and this is what is called as Amdahl's law. Okay, so what we have looked at it, what I explained it informally. This is what is called as an Amdahl's law. What I would like you to do is I would like you to go and read what this Amdahl's law is about. Okay, can you make a note, because you may get it in the exam asking you to explain what Amdahl's law is. So make a note of it. So similarly, you can use Valgrind and perf. So the problem with let me see one thing. Let me clear this. There are other two tools, clear all drawings. There are a couple of other tools which are so the other two tools which which we mentioned is Valgrind and this what is called as a perf. Let's see if perf works. Perf dot can someone just give me a minute? So trying to figure out how to use perf. Look, I forgot the options for the perf. Okay. Let's see. So perf is another tool called start dot hotspot dot gen. Okay. So you can see using perf, you can see that the number of instructions per cycle is 0.61 instructions per cycle. Remember, this is what we were looking at in the last class or before class, where we were trying to see, we want to see that the number of instructions per cycle should be way greater than 1, because we are using a superscalar processor. But in this case, it so turns out that the number of instructions per cycle is very low, 0.61 instructions per cycle. Or then, so actually, using perf, we can yeah, like we can measure so many things. Right now, yeah, I forgot some of the options. Maybe in the next class, I can demonstrate how powerful perf is. But some things I would like you to understand here is like, for example, you can see the number of context switches. So if there is a lot of load on your system, then what happens is the number of CPU migrations, the number of context switches, etc., or the number of page faults, this increases, and they will have an impact on the performance of your program. Okay. Are you all with me so far? So perf is a very important tool. So perf is supported by the hardware because the processor will have what are called as performance counters. As your program is executing, what happens is the processor makes a note of different statistics, and those statistics will be reported at the end. So perf is a very important tool because it can without the kind of intruding into your program, it is possible for the program to it is possible for the processor to give various performance statistics about the program. But as against, if you want to use gprof, you have to use GCC minus PG option where code gets instrumented. So this is what I want you to really appreciate here. Very important. So when we use GCC minus PG versus perf, okay. So here program instrumentation happens. Program instrumentation. Okay. And here, what happens is instead of program instrumentation, so this is what are called as hardware performance counters. So that means you don't need to, if you want to analyze, for example, LS program or some random program, you just have to say perf LS, okay, perf stat. Yeah. Okay, if you just say perf stat, you don't need to compile the code for LS or any program that is given to you. You can just give it to perf, and using the hardware performance counters, you will be able to get an understanding about what all the things that are happening in that program. But you will not be able to do a gprof of LS because you need to have access to the source code, and you should be able to compile this code using minus PG option. So source code access is necessary. Source code access necessary here. So here in the case of perf, no need. So here, no need of source code. Okay. And then there is this third thing which is called as Valgrind. So you can use Valgrind, but Valgrind is a virtual machine. So it will be able to do whole lot of performance analysis it will be able to give. Like for example, Valgrind has something else as a submodule which is called as callgrind, which gives very detailed call graph analysis. But what is the problem with Valgrind versus GCC versus perf? Can anyone tell me what is the problem with this? Sarchit uses it to find memory leaks and segmentation faults. Great, very good. What is the problem? Do you see any problem, Achit, since you use it now? So this is one. GCC minus PG is one approach for program analysis, and Valgrind is another approach, like all these colors, and then perf is another approach. So this is a short question in the exam. So what is the differences between GCC, perf, and Valgrind, and what are the pros and cons of using them? Okay. I want you to, in the next class, I will I want you someone to get back to me and tell uh, what is advantage or disadvantage of using Valgrind against perf for GCC minus pitch. Okay. And then we will note there are a couple of things where I really wanted to you needed the GCC needed GUI. That is, one is called let me clear my screen. So one is called as Intel VTune Analyzer. This gives a very detailed profile picture. This Intel VTune Analyzer. So like for example, if you want to analyze the dot product program, so there are different ways of so there are different analysis we can do using Intel VTune profiler. And there is one more super duper tool which is called as an Intel Advisor, using which we can do what is called as a roofline analysis. So these are the two things I would like to discuss with you in the next class. One is how to use VTune profiler, and the other one is Intel Advisor. When we look at Intel Advisor, we get a very detailed analysis of the roof lengths. So that forms the foundational basis for figuring out how to optimize our program. Where are the bottlenecks, compute bound, memory bound, all those things we will be able to understand using Intel VTune, Intel Advisor. Okay. So these two things we will take up in the next class. And that's all from my side for today.